at Rutgers University Libraries. In this video sequence, we are going to be talking about machine learning with Amarel using R. Now, there's a couple of things we're mixing together in these workshops. We're trying to introduce people to the Amarel high-performance computing environment at Rutgers, which is supported by the Office of Advanced Research Computing. And we're also talking about just how to work with large data in general, and how to clean and begin to analyze that type of data. So there's some machine learning. It's not very detailed course in machine learning, but we are providing some introduction in that direction. So the first video, this one that you're listening to right now, is we're going to talk about Amarel and the high-performance computing environment at Rutgers. It's going to be relatively brief because, as I will mention repeatedly, the Office of Advanced Research Computing, OARC, provides their own training resources, their own videos that are much more detailed than this. And so consider this an introduction and an invitation to go to OARC, sign up for their events, and start to learn more. So I'm talking about Amarel. Amarel is the major cluster for high-performance computing, which is generally available to anyone at Rutgers. Anyone at Rutgers can get an account and start using those resources. So if you have one URL that you want to jump off from, it is this GitHub site, github.com/RyanData/AmarelR. That's also linked in the description below. That page links out to the things that I'm going to be talking about here. So it links to the OARC page on Amarel. That cluster is named, by the way, in honor of a Rutgers computer science professor, a founding member of the computing science department at Rutgers, Saul Amarel. And you can see more information on the OARC site. Let's take a look at the OARC site right now. So this is the Office of Advanced Research Computing. You can see they lead with Amarel at this point. There are some other resources and clusters that they maintain, such as Caliburn, but let's just stick with learning about Amarel for today. For an account, and it'll take you to a form to request access. You do need to provide some information about what department you're coming from, what kind of research or uses you plan to have for Amarel, because like all organizations, OARC also has to justify its impact, its significance to the Rutgers research enterprise. So do your part and let OARC know how you're going to be using this resource. Something that people ask me often when they're signing up for this is this field for name of the PI of your research group, the principal investigator of your research group. So Amarel has dedicated resources for certain research groups. If you are working with the research group, providing this information lets OARC give you access to those things in a very streamlined and organized way. So that's a good idea if you have a PI, but you don't need to fill that in. So you don't need a PI, you don't need a PI's approval to use this system. You can just use it on your own. That's perfectly fine. And that's one of the things that's not required here. Another key caveat is you cannot use Amarel to work with confidential or sensitive data. So health information, for example, that's under HIPAA restrictions, this is not a place for that. It does not have that kind of security setup. So please be aware of that and do not use it for any kind of sensitive data of that type. So signing up is easy. You should get a relatively quick response in a couple of days to that request, and you'll have an account set up on the system. In order to use Amarel remotely, you have to be on the Rutgers network So what does that mean? If we're trying to get to the Rutgers network remotely, we need to be using the VPN. So the VPN instructions are, if I keep track of my tabs, at this little window, I have a guide to some of the links and things that I'm talking about. So the GitHub site, the OARC site is just oarc.rutgers.edu. And this VPN site is via the Security Operations Center, soc.rutgers.edu/VPN. If you have not used the VPN before, you must activate it with this button. In order to connect to the VPN, once you have told Rutgers that you'd like to use the VPN, you will need to, at the time of this video, again, I'm going to caution people that I'm not planning to just update this video every time there's a small technical change. So please check the links for updates, check for the latest requirements. But at the time of this recording in April 2021, you will need the Cisco AnyConnect client for your device. And you will also need to use the paired Duo app in most cases along with that. So those products kind of work together. Duo is the two-factor authentication system that supports this. So you would install the Cisco AnyConnect client. And I'm not going to show that here because I'm actually recording on my desktop computer that does not connect to Rutgers. So I'm not going to walk through this. I will point you to the resources that will help you with that. But get the Cisco client, launch the Cisco client. When you connect to the VPN, it's going to ask for your NetID and password, and it's going to ask for some other token of authentication. So if you install the Duo app, I think for 95% of users, it will be most convenient to have the Duo app on your phone. And the Duo app on your phone will that you'll be able to tap and say, yes, I approve the logging into the VPN via my phone. So we now have proved to the system that you are someone who owns your own phone, your personal phone. You've provided that second authentication token, and you'll be logged in. So once you're on the Rutgers network, you can use a terminal shell just in sort of raw format. I'm not on the Rutgers VPN. It's not going to find these resources, right? Rutgers VPN, it's not going to find these resources right now. You must be on the Rutgers VPN to connect. And I can connect via a terminal. I can also connect via what's called the Open On Demand system. And if you Google Open On Demand, you'll see that this is a common platform for shared computing, which Rutgers has a copy of it installed on the Amaral cluster, and you can go to it by going to ondemand.hpc.network for that address to resolve. What this will give you would be a graphical. What this will give you would be a graphical environment that can support things like RStudio. It'll support a Jupyter notebook, and so you can interact more easily with the jobs running on the system. You can also just get a plain desktop if that's what you'd like. That's the way you'd prefer to do your work. So the on-demand system is available. The terminal access is available. And I think at this point, I would just like to emphasize the training resources that are available from OARC. So if you go under Help and Support here, you'll see there are there's FAQs, which answer a lot of questions as well. There are, and let me show you the most important FAQ. If you still have questions, you can actually write directly to help at oark.rutgers.edu, and they can work with you on any kind of specific needs of specific software, different kinds of resources, any hang-ups you're having. Very helpful team, wonderful team that's working there. So if we go to the tabs under help and support for training and scientific consultation and the technical user guide, those two are what I would call the sort of prime places to get getting started training material. So OARC has their own workshop calendar that you can click and sign up for workshops. They have a regular series of what are called weekly open workshops where they discuss various topics, and they have periodic intros to the Amaral cluster, intros to the Linux command line system. So those are things that will help you get started and dive in and using the system. Also, there are recordings of these videos available here, so you can just click View Now, and you will get access to the past recordings of these workshops. So there's really quite a lot of very interesting content here. The open workshops cover a lot of different software, a lot of different topics, and you can actually, specific topics like R or Python or other tools that you might want to use on the cluster. They're very informative. GIS. Recommend, highly encourage those. The other thing you'll see under the technical user guide, is the full details of all those nuts and bolts that you need to work with the system. So where are the files located? A couple of general cautions, right? So when you log into Amaral, you will be placed on a login node that's shared by everybody logging into the system. As they say here, do not run your research applications on the login node. You are going to slow things down for everyone if you do that. You want to take advantage of the cluster and run your jobs out on the cluster via the Slurm job scheduling system, SLURM, which you can again find help on that from OARC, from their training. You can also Google Slurm and you'll see some user guides to that software. From a very quick introductory point of view, there are really two main commands that you're definitely going to want to know about there, srun and sbatch. So srun submits a single shared job, and the basic example that's here on the cluster user guide is this line, srun python-c print, right? So we're asking Python to run this print command to calculate the product of that multiplication and return it to us. But we're not doing it on the login node. We are doing it via sharing the job out to the system. So it puts the job in a queue. It'll give you this notice that it's waiting for resources, and then when it gets the resources, it runs and returns a result. This will happen really quickly, less than a second, usually for some fast operation like this. But the process is the same if you have a large job that is going to need a lot of memory or a lot of nodes to run. It'll be put in the queue. The Slurm scheduling system will look for a place on the cluster that has sufficient space to run that. Put it, queue it up. When the time comes, it'll run the job and return it back to you. More advanced, brother of that command. I'm going to scroll down a little bit to show an example here. sbatch comes with a lot of settings that specify the amount of memory, the amount of nodes that you're requesting, the amount of time you would like the job to run. We can queue all that up, and then we can submit a batch file, so a script in R or Python or whichever, just a shell script in any sort of command line file that you want to run gets submitted. And this would be a preferred method for really larger jobs. And we set it up so that the output of the relations or whatever we're doing is put into an output file, right? So we can submit this, let it just run whenever it feels like it, and check back later for the output. We've got everything taken care of. If you go to the OARC trainings or watch their videos, you'll see more detailed examples of that. So srun, sbatch. You can also, again, as I mentioned, use the GUI system, the Open On Demand system, which will look and feel much like tools you're used to looking at, like RStudio. Once you launch an RStudio environment in the GUI cluster, you'll be essentially in RStudio. And the final things I'll mention here before closing off this video is discussion of the file directories. So you have a home directory where things are kept on a long-term basis, but it's not the high-performance big area that's very fast and accessible. There's also this Scratch directory, which you can put very large files in. It's just be aware that it is not permanent. It is not backed up. If something gets messed up there, you'll have to recreate it. And this is not a long-term storage. Scratch, as the name would imply, is not a long-term storage area. And you may be interested in some of the other aspects here, but home and Scratch are what you need to know to get started. And in terms of navigating around those directories, that's sort of Linux/Unix basics, which I'm not going to cover in this video. You can follow up with training. You can use the pre-installed software on the cluster via their module system, but you may also want to install your own software, and you're perfectly free to do that. As you would on a Linux system, you can pull files and run the install scripts. So that's described here. If you've done that in a Linux environment, this is going to be relatively straightforward, except you don't have root access. Be aware of that. If this is new to you, then I would encourage you to sign up for some of the training and reach out for additional help from OARC on that. There are actually quite a lot of options, but it is more of a do-it-yourself system than you might be used to if you haven't done this kind of thing before. But working with the OARC team, I'm sure that you'll be able to find the tools that work for you and configure the tools that work for you. So just again to review, we have talked about getting connected via the VPN, Cisco InConnect, and the associated Duo app. We've talked about getting an Amarel account, the types of things that you can do once you log into Amarel, and again, always the additional training that is available from OARC. So I'm going to stop here with that introductory material, and the next video we're going to actually get into RStudio and start working with data, because that's the main event here. We're going to work with some large data. So thanks for your attention, and or jump over to Hello, welcome back. This is Ryan Womack, Data Librarian at Rutgers University Libraries. This is the series on machine learning with R using Amarel. In the first part, we looked at the Amarel specific details of how to connect to Amarel. And in this part, I'm going to, or this and the subsequent parts, we are going to run through an example working with a largish data set and how to handle data at that scale, how to merge, how to filter our files, and then we're going to talk about some machine learning techniques. This is not a comprehensive or detailed as an introduction to try to get you started, give you some things to think about in that direction. So with that said, I'll just jump in, and I did a run through of this earlier where I tried to do everything live in the video. I found that due to the size of the files, my audio was having trouble keeping up. When my system ran out of memory working on files, my audio began to drop, and so I'm going to pause a bit more frequently than I normally would and talk about some things that will run in the background to try to make this a more compact video series and one that will hopefully function better for you. So I'm using the file amrel.r. So we are working from the GitHub link that is in the /github.com capital. If you go there, you'll get links to these other capital. If you go there, you'll get links to these other places. Go there, you'll get links to these other places that I'll be referring to, and so just leave that up on the screen for just a moment. That's also in this descriptive link. So the links here talk about OARC and connecting to Amrel. For this session, we're not going to be running on Amrel. We're running on my home machine, which is not hooked up to Amrel, so that we can have clean focus on the code and not worry about some of the Amrel specific details. It's a bit tricky to do all of that and record at the same time, at least the way I have my setup. So it could be run on Amrel, and you could use the tools that are available there to do it, but we're not going to do that for this session. So we are going to focus on this New York City parking tickets database, which is available from Kaggle. Kaggle, a very popular activity, including some contests, some shared code competitions, things like that. And you can go to Kaggle, you can find a lot of different data that's been uploaded. A lot of it has notes or discussion there, and you will have to create an account to sign in and download the data, but that's a pretty easy step. I would caution you, the data on Kaggle, a lot of it is great. It is user uploaded. It's not an official source for anything. So, for example, you may, if you were really interested in what's going on in New York City today, you'd want to go and locate the official source from the New York City Department of Finance, look for updated files, things like that. Project, and it's frozen in time. It might not be that complete. The documentation for this particular data set is not that complete online here, and we'll be discussing that just a bit. So there are 4 files, one for each fiscal year ending in 2014, 2015, 2016, and 2017. So our code is going to merge those files together. Each individual file is about 2 gigabytes, and we're going to merge them together into one 8 gigabyte file. So preliminaries, I am just going to load all of these R packages with the library command. If you don't have any of these, which you might not if you're doing this for the first time, you will have to run through and install them, but in the interest of time, I'm skipping that step. I've already installed these packages on my R system. And in my case, I have moved these data sets to my local home directory. So for a little while, I'm going to set my home directory to that. On the Amrel cluster, these data are available to you if you were to set your directory to, just make a note of this in the code, it's in the Scratch directory, and I've made them publicly accessible so that you can, if you'd like to work with this data on Amaral, you could just use them directly from there without having to download them from Kaggle. So on your own computer, change it to your own local directory wherever you have the data. Now this is local directory wherever you have the data. Now this is where I'm going to talk through this a bit, and I'm going to wave my hands around because when I actually load these files, this is where I found it was messing with the audio. So when my memory got full, I'm now actually working with a completely fresh start, a rebooted computer to deal with maybe some of those memory issues. I have 32 gigabytes of memory on this machine. It's enough to complete the analysis, but it seems like when I'm trying to run something else at the same time, like the screencast, has some unwanted side effects. So I'm going to talk about this, these steps. In particular, if you're on Amaral, you would need to install these 3 packages just to get through the sort of data merging step. And again, I'm just going to add some notes here as we go through. What you can do when you're working with this data on your own is you can compare what happens when you load the data via different approaches. So there's the standard R read CSV command. And if you read these in, you'll find that for these 2 gigabyte files, it actually is fairly successful, but it's maybe takes about 60 seconds per file to read those in. When we try to use the tidyverse's read underscore CSV command and load the data into a tibble format, the load is a bit slower, but it still completes. It's all right. I would call it, a little bit annoyingly sluggish at this scale. But the package that is the most useful for big data, and I think that's probably the case for anything that's like a gigabyte and larger, you start to notice this sort of ease in performance, is the data table package. And that has a command called fread to read data in. And I'm just going to run one of these right now live. And the rest I'm going to do some hand waving over off camera. You can see that the fread package has a nice progress bar, which will tell you how the loading is going. That's good, especially when the file is large, to see that yes, something is happening. We can see that our memory bar is starting to increase rapidly as we load these files in. And you'll see that it loads, and then it takes a moment to actually populate in the global environment in the top right. So everything about handling these larger files reminds you that there is, these steps behind the scenes where things are being moved around from block of memory to block of memory. So in order to merge this data, I'm going to load all 4 of the yearly files. When I examine the data, I notice that 2017 has fewer variables than the first 3. So I want to compare all 4 years. So I'm going to throw out the extra variables on the first 3 years. So I'm only keeping columns 1 to 43. And then there are 3 variables that have some missing data. They're just not easily comparable across all the years. So I did spend some time examining the data that I'm not showing in the video here. I'm just removing those 3 variables, just with a very basic, almost primitive kind of remove column number command. So because these are large files, I'm then going to merge the data in two stages. I'm merging 2014 and 2015 together to create a 4 gigabyte file. Then I'm saving some memory by removing those 2 gigabyte individual year objects from the workspace. Then I'm going to merge 16 and 17 together, remove the 1 year files, and finally merge together each of the 4 gigabyte files to create one 8 gigabyte file. And then remove all of my sort of other steps along the way. So I just have one 8 gigabyte file sitting in my memory. So I'm going to do that off camera so that we can hopefully avoid the recording issues that I experienced before. And so I'm going to break the video here and come back once that step is complete. All right, now we're back with part 3, and while a few minutes have passed, I have merged those files and removed all the intermediate steps. I now have one single file called parking with 42 million observations of 40 variables, and I'm going to perform another step here, which is to take a 1% sample. I'm going to just hit enter there so I start running the command. And we're taking a 1% sample so that we have a smaller unit that we can actually start working with and have very responsive commands. When we have this large-scale data and we're just exploring it, we don't want to wait for 2 minutes for each command to complete until we decide that we're really ready to do our final analysis. It's always very useful to work with a smaller sample, and in particular for this video I'm going to be relying on that a bit more than I normally would because I want to make the video concise and not bore you to tears with waiting too much, even though there's some element of that in this video already. So you can see that command is going to run for a little while. It does have to loop through those 42 million observations, and I should also note while we were gone, as I worked with those files, I gradually got up to my 32 gigabyte memory limit, and one thing that happens is when we get near the memory limit, a lot of time is spent out swapping, doing a lot of swapping in and out. You'll note that it hovers above 32,000, but the hard limit is 32,100, so it's always taking in and out little chunks to the swap space so that it can manage that. And once it completes a step, it may be able to free up a big chunk of memory, and that speeds things up a great deal. This is the thing that I'm nervous about. That is the kind of thing that might start interfering with the audio recording if the computer gets a little too busy or overburdened. So this is one step I'm doing live. I might avoid some other ones in the future. Okay, so as an aside, if you're working with this data on Amarel, you can skip the merging part and just download my pre-created samples, which are in the Scratch directory if you use these paths. So if you were having trouble with the merge, or that didn't appeal to you, you can do the rest of the work here just by grabbing the data with the code on line 109 or line 116. Write CSV to export data and make these CSV extracts available. That's pretty standard, but it's worth mentioning. So through the rest of this analysis, we've created our parking file, and that's the full data set, and we're going to be working with this parking sample, this 1% sample, for most of the other code. Anytime you want to check how long does it really take when I go against the full data set, just plug in parking in the code instead of parking sample, and you can check that yourself. So this command completes, which I hope won't be terribly long. I won't be terribly long. I will wait just a moment for that to come through. This again might be a product of us being near the memory limit. I think if we weren't near the memory limit, the command would have completed much more quickly, but we have that effect to worry about. That's one of the big data issues that we have to worry about. Again, if you're working on Amaral, this is a case where requesting the correct amount of memory is very important. Give yourself some overhead. I might even request 64 gigabytes just so that when all these intermediate steps run, we're still left over with a good deal of overhead beyond that. About what's coming up, so that we can again skip ahead once the computation completes. We're going to look at the parking sample data, and then we're going to try to generate some correlations to see which variables are related to each other. However, we can't run correlations against non-numeric values. So you can then take a step back and just run individual tests of one variable against another, making sure that each of them are numeric with the core test function in line 132. But another approach is in lines 136 and 137 that we actually create a no-character subset of our data that has all of the numeric. So my parking sample has now completed, 423,000. Sample has now completed, 423,000 observations. You can see that took 2-3 minutes to complete. And now when I run something like a summary, I can run it against the parking sample, and you can see that that's fairly responsive. If I ran the summary against the full data set, you'll get some results, but it still takes a little while. Now I can see what's going on in each of these variables. I have a lot of sort of technical things like the street codes, vehicle body type, vehicle make, precinct where the tickets were issued, time when the ticket was issued, and so on. This data set is both detailed but also doesn't have a lot of things we can use for like cause and effect relationships, so that's one of the things we'll see as we go through. I'm going to attach the parking sample data so that we can refer to the variables easily, but keep in mind that when you attach something, you're creating another copy in memory. So that would be a bit of a dangerous thing to do with the full parking data because you're asking for another 8 gigabytes for this attached copy, which again, R can manage that by swapping in and out to some extent, but it's still a little bit difficult. So as I mentioned, if I run the individual correlations, I can do things like the code, which is numeric, something like, and see if there's a correlation, and I'll get this correlation of 1.17. I'll get this correlation of 1.17 or 0.18 rounding up, and some other statistics letting us know what is the confidence interval around that estimate, the p-value associated with the estimate, and so the core test function gives us that, whereas if we just say core, we only get the correlation. So just to show you that. 0.178. Okay, so now I'm going to run the removal of the that's only a quarter of the size of the other ones. Actually, probably a little bit smaller because some of the character data takes up more space. And you'll notice it did it really rapidly for the sample, and actually did quite all right for the full parking data as well. Apparently that operation of just dropping the columns is more easy for R to process. So now I can do a correlation matrix of the entire data set with an option that says use the pairwise complete observations. Right? This doesn't handle not available data well, so we want whenever we're dropping the NA data, but we're not looking at just the complete cases that have no NA data for the entire observation, but just pairwise. So when we match summons number versus violation code, only if there's an NA in either of those two do we drop the observation. Okay, so this is a matrix, although it doesn't really display that nicely on screen. We can see there's a 1 along the diagonal axis, but this is a little, we could peruse that, but it's a little messy to take a look at. What I'm going to do next is use the GG core plot package to show you a visualization of the correlations. There's a link here to more about that package, and this works in a grid, and color codes it so that we can see the strong positive relationships in dark blue, the negative relationships in red, and we can get a sense of which of these variables might be strongly related to each other. But just the significance, we can do it this way with a this actually has an X through the things that are not strongly correlated, which reveals that there are only really a few variables with strong correlations in this data set. So we're just kind of looking around at our data. One thing to note if we look at this data, there's a 1-to-1 correlation between violation precinct and violation location. So that suggests some collinearity. We're definitely not going to want to use both of those variables at the same time. I'm not going to pursue that right now, but that's something just to note. And something that does have a strong but not identical correlation is issuer precinct and violation location. So the violation precinct is probably a superset of the exact location of the violation, but the issuer precinct, that's who gave the ticket, that can come from nearby, can come from a neighboring precinct. So there's a connection there, but not as close. We can also do things like our traditional regression on particular variables and see a little bit more of what kind of relationship there is. So this is a significant relationship. It explains some of the variation with an R squared of 0.28, and as the issuer precinct goes up by 1, the coefficient implies that the violation location would go up by 0.3. Look at this data primarily because it's a largish data set. If you want to understand the data, that's its own thing that's very important, but we're glossing over it here. I give you a link to the map of the police precincts, right? So we may want to understand something about those precincts are numbered, right? But if we understand where they are in New York City, we would maybe be able to categorize them in different ways. They're probably different ticketing patterns in business districts versus residential districts. And there's a lot of things you could do with this data once you bring your own knowledge and analysis to it. So I don't want to, that's a very important thing to consider, but unfortunately we're not doing it here. So I'm going to run through a sample of the code up through 300. So we're just doing two more things really with the code. We are doing some histograms so that we can understand how this data is distributed. Error saying that the data is nicely. The summons number is a very large sort of code with numbers up through 85. Is that 8 billion if we're reading it as a number? That may not be a meaningful thing to plot as a histogram. So you're going to encounter this in large heterogeneous data sets that not every variable behaves the same way, is the same kind of thing. Knowledge to bear. Here's the violation code. We can see that there are certain violations that have a lot more tickets associated with them than others. And again, we'd want to dig into a guide to what those violation codes mean so we can figure out why this high 30s. What are those violations for? Is that overtime parking at a meter or something different? So this is the vehicle year is interesting because if we look at the summary, there's a minimum of 0. So actually there's a lot of data that had no vehicle year, but instead of entering it as NA, they entered it as 0. If we want to get a good computation of the vehicle year, we'd have to fix that, right? We'd have to go in and correct and replace the zeros with NA. We can see that the maximum year is 2069, so that's obviously like a typo. And we want to screen out any vehicle years that are beyond the present. We can probably guess from the median a little bit better what the average age is, but here the mean implies a mean vehicle age of 1533, but I don't think there are a lot of ancient carts on the streets of New York like that. So again, this kind of basic data exploration can let us see what's going on. We can even do something like this slice sample on line 189 so that we can just pick a few random rows from the data. That's what it does. And we can actually delve in. We obviously can't look at 42 million rows of data, but if we sample it a few times just to get a feel for what each of those row observations is, that's a better way than looking at, say, only the first rows. First rows might not have the same pattern as the entire data set. So you can use this slice sample and set an N to pull some things out. The Broom package also has this glimpse function that does a quick view of the so that may be another quick way to take a peek at what's going on. Looking at this, we notice that the last three variables are pretty much, there's a huge number of NAs in those entries. So that's not good for our other data analysis, and so I'm going to do one more cleanup step with taking the last three variables out of the data set. And so we've Instagram one. Just want to make sure we're still going with our recording. Environment, not up at 30 seconds. I know that this will be able ranging on line 2. It's 18 for have an overwhelming number of entries, a little more under 66, and we have the western states that are far away, less likely to get a ticket on the streets of New York. Some of the codes are for non-U.S. states, so I'm not familiar with all those, but you have things like ON for Ontario, so you can have Canadian ones. And only when we get to northeastern states do we have really high frequency. So New York, obviously the bulk, New Jersey about a tenth of the New York level, then Pennsylvania, then Connecticut. So I'm surprised actually that Connecticut, not as many people drive into New York, or maybe they just know the parking rules better, but the number of New Jersey tickets dwarfs the number of Connecticut tickets that are given. Florida, Massachusetts, etc. Some of these that are more abstract, like the violation code, are just these numbers that correspond to the code. So we can again see that 21 has the most. So we'd have to go and look at the parking violation. So we'd have to go and look at the parking violation to see which of these, what the meaning of violation code 21 is. Meaning of violation code 21 is. And then finally, let's look at vehicle year. So again, we can see how many of those zeros there are. So some of these, you can see there's a data quality problem that people enter, instead of 1986, they just enter 86. But there's a relative handful of those. It's not a huge number. And this is an issue you're going to face with any big data set, is how much cleanup to make it perfect, to make all 42 million rows perfect, is going to be very difficult. How much does it matter to you? It's probably going to matter to you to fix this 7, right? What does that mean? 7 is that, sorry, I actually scrolled to the wrong spot. Oh, excuse me. So I'm actually talking about something that hasn't been displayed yet. So actually there weren't any single-digit vehicle years. I was talking while looking at the violation code. So ignore what I just said. There is still a data quality problem. I can be confident that in a data set this size, there's always some data quality problems. So the general point remains. We've got 2063. That's, what does that mean? Was that 1963 and it got accidentally entered as a 20, or did someone mean 2013 and the maybe the handwriting was scanned and the reader didn't get it right? But we have just a handful, right? We have 1, 2, 3 observations here. Maybe that's not important. Maybe we can just drop all those and not pay attention to them. But if we have mistakes that influence our main point, in large numbers, that's where we have to be careful to understand the data. So here, as we saw, there are 100,000 tickets that have a 0, and so I would probably interpret those as an NA, but it's something that you'd want to question yourself about how you're going to handle it in the data set. Comparison, this final 297 to 300 table is 297 to 300 table is run against the entire 42 million data set. And you can see it did hesitate a moment before it produced a count, but it actually does some of these counting operations pretty quickly. So it was able to count and rank and sort the entire data set pretty fast. And we can see the pattern actually is very similar to what we saw in the sample. That's good. We'd hope that the sample is representative of the larger group with the same kind of ranking: New York, New Jersey, Pennsylvania, Connecticut, in terms of number of tickets. Okay, so all of that is all about getting to know your data, exploring on a very basic level, You do want to look at each variable, understand what's going on, because that's going to affect what you insert into your actual models, which is coming up next. So the subsequent part, next part, we're going to get into the machine learning aspect and stay. Okay, welcome to part 3 of machine learning with R. And in this section, we are going to actually get into our machine learning techniques a bit. Once again, just want to remind people this is a very introductory exploration. We're not going to be very comprehensive, and so there are plenty of machine learning courses online that you can pursue in greater detail. This is just a kind of warm-up, getting you started with those things. So first I want to talk about k-means clustering. So k-means is a method whereby we pick a certain number of centers, k is the number, and we attempt to group the data into clusters around those centers. And so the algorithm starts with random center points in the data, and then tries to move the center to minimize the distance to other points in the cluster until it converges on a good fit. And so this is, an approximation technique. It doesn't have a deterministic outcome unless the data is strongly clustered on its own. Then it will often arrive at the same outcome every time. But you can expect to see something different every time you run this algorithm, every time you iterate. This is just an illustration of the idea of the clustering. And so we're going to look at that in the R context. A couple of things to note: that it requires numeric variables. We're computing a Euclidean distance, so we can't use character variables, factor variables. Unless you wanted to convert them to numeric measures, you could do that. So I'm working with the no character data extract that we constructed earlier. And I also have removed the elements for summons number and street code, because those are not particularly interesting. They are just sort of ID type numbers that we don't have a strong reason to associate any causality there. So I've removed those to simplify things. And then finally, I have rescaled the data. So because it's a distance metric, right? Think about, we're measuring something like feet from the curb. If we measure that in millimeters, we're going to have a very large magnitude number. If we measure it in meters, it'll be much smaller. If we have two variables, one measured in millimeters and another in meters, the millimeter one would be way overweighted in our calculation just because of the scale. So we have to standardize the data, which sets the mean to 0 and the standard deviation to 1 across everything. So just the easy way to do that is to apply this scale function. So I'm using the tidyverse mutate step and scaling each of the variables in our collection to create a new rescaled data set. So rescaled parking is the small sample. Rescaled parking 2 is the large sample of all 42 million observations. Now, I've run this off screen before starting to talk because the rescaling of the full data set is a little bit time consuming, and again makes me a little worried about my processing overhead. So all that I've already run, the lines from 302 up through 340. Now I'm just going to show you 340 so that we can see that when we do a summary of the data, we can see, yes, it has been rescaled. All the means are 0. It looks like it worked as advertised. So then we can go in and actually look for the centroids in our data. And if I do that for the get an error, k-means data can't deal with not available data. So this data can't deal with not available data. So this is a problem for us. We're going to have to deal with that. And one way to do that is to use the NA-omit function. So this is on line 347, which screens out the not available data and gives us results from a clustering. So we have, in this case, clustering with one cluster much larger than the others relatively small, and the smallest only 7,000 out of the 433,000. There's a report on where the centers lie. It's a bit difficult to draw a judgment from that, especially the nature of this data. And then the clustering vector shows us, for at least the first 1,000 observations, which cluster each observation falls into. We're going to see another visualization of this in just a moment that'll give us a better feel for the data. And in this case, the sum of squares by cluster tells us that the 99% of the variation in this data is between the different clusters. So we've actually screened out a lot of variation, but you have to be a little cautious of that. What did I do here? I ran the k-means on the non-scaled data. And so that means that these very high numbers, like the issuer code, are going to be the important variables for contributing to the sum of squares. The numbers like feet from the curb that are relatively small are not significant in this case. So probably the clustering has just taken care of issuer code and not worried very much about the rest, which is why it reports that it's got this great fit. And so that's an example of something that you should not do when you're working with this kind of k-means data. So when I run it on the rescaled data, you can see that the amount of variation that is between the clusters is now down to 42.6%. So that's 42.6%. So that's a moderate fit, but a much more realistic fit than 99%. And in this case, the sizes of the clusters are quite different. They're much more equal in size. The measurements on the centroids look fairly different, although I won't go into detail about that. Just a very different character of result. So we have that. I will run just one time, so you see that it takes a bit of time, is running the k-means against the full 42 million observation data set. Now this is, it's an iterative approximative process. It is, so there's a lot of computation going on, but we can see that it does succeed in eventually producing a result. So I'm going to let that run for a bit and talk ahead in the code until this process finishes. We'll see about how long it runs. So what happened here, as we mentioned, k-means cannot work with not available data. If we believe that the observations with not available data are important to us, we may not want to just drop them out, right? So we may want to impute the values for those. Impute means you're making something up to insert instead of the not available data, but you're making it up according to some rules. Sometimes people use the mean, sometimes people use the median of the remaining data, which are basic methods. You can do those with the R package hmisc. There's also the mice package, which has more sophisticated methods. And there's actually a book by Roderick Little on missing data that, if you really want to dive in and study all of the methods to deal with missing data, I'd refer you to that. So now we see our result did succeed in clustering the full 42 million observation data, and we've got cluster sizes of 13 million, 14 million. So pretty interesting that it's able to do that in not too long. And we have cluster means. Let me just look at the numbers for violation code. So 0.07, 0.27, 0.21. Is that very different from what we found before? Yeah, very different centroid points, right? So this is again, when the data doesn't exhibit its own sort of strong structure, the clusters can form in a number of different ways. And here we actually explained more of the variation of the data, 51%. And again, dealing with data at this scale, it's very hard to tell a simple story of the causality of why that is. But you'd have to delve in and iterate to do that. So I'm going to mention a method for iteration in just a second. So when I want to examine, going back to the issue of the not available, the missing data, I can check whether I have missing data for observations with an isNA function. And I can do that variable by variable and do a table. So lines 360 to 366 are this quick check. And I can find that, okay, violation location has 64,000 missing items because missing is true. But for the remaining variables, there are no missing observations whatsoever. So in this case, I'm going to conclude that the easiest thing to do is get rid of that one variable that has missing data. And then we will have a complete data set that no longer has anything about the violation location in it. So I've just dropped that column in lines 370 and 371. Scaled data as well, parking 2, parking 2, on parking 2 again. Let's do that. Something a little different. To get around this issue of the random starting points, we can just iterate and we can run multiple tries. So there's a parameter called nStart that I can specify. So when I say nStart equals 5, it's going to run the k-means algorithm 5 times instead of just once and average the results so that we get something that's hopefully less sensitive to the random starting point and more representative. You can see that for the 400,000 observation data, this still takes a little time, right? Because we're doing it 5 times. I certainly am not going to run this for the 42 million observation data set because that will definitely take much longer. But we should have a result for the smaller data set. Yep, here it comes. Let's just look at that cluster size. And this, interestingly, even though this is the rescaled data, has given us these unbalanced cluster sizes. One of these clusters is quite small, 7928. And again, we could go back and compare the cluster means. And if you're running this analysis, you would want to basically iterate as much as you could in order to get a robust result that's not going to be sensitive to change. And again, it's more of a judgment call, your kind of cost-benefit analysis of how much time do you have to work on this versus the significance of improving your result or making your result more robust. So again, we're hovering around 50% variation explained by the difference between the clusters, which is all right. That's okay. To visualize this a little more, we can only visualize in 2 dimensions. So I'm going to just look at this defined feature set of violation precinct versus issuer precinct. So just those 2 variables. And I'm going to create a clustering just on the basis of those two variables instead of all the variables in the data set. So if I try this for the, and this will show you the difference again between the scaled and non-scaled data. So the first try of this is going to be for the unscaled data, which I'm calling my K, and the second try on line 391 is for the scaled data, which I'm calling my K scaled. Now, the results of that we can visualize using the facto extra package, and the command is fviz cluster, and there's a link here if you want to learn more about this method. I've just kind of applied that technique from that blog post, and with some settings, to determine your look and feel of the graph. fviz cluster does the work of visualizing how the k-means data is clustered. And here comes our result. So still, even though we're just working on the sample data, still a little bit large to do 400,000 points. And you can see the clusters are fairly kind of imbalanced, right? There's this huge number down at the bottom left. Then there's another segment, and there's a few outliers with this high number of violation precincts for violation precinct, but it almost seems like the data is dominated by how close it is to the origin. Like there's points close to the origin, there's another group not so close, and then dominated by the non-scaled nature of the data. When we look at the nature of the data, when we look at the scaled data, we actually get a different kind of result. Well, maybe it's not that different. It's still dominated by this point close to the origin. Note that the clusters have sort of switched number. I mean, it's cluster 3 now near the origin. The number of the cluster is actually kind of arbitrary, right? That's random. So we don't assign meaning to the fact that it's the first cluster or the third cluster. It's just an arbitrary label. Again, it's a complex situation, and we have these numbers that are not scalar. Right? The precinct is just a label for something. So there's a connection between the violation precinct and the issuer precinct, as we discussed earlier. This graph maybe gives us a little bit more insight into it, but I won't try to push a narrative onto it. We can try this for other features. So for example, if we look at the violation precinct versus feet from the curb, are there different groups? Like in certain areas, do people park further away from the curb or not? Is there anything we can say about this? The unscaled data reveals a pattern that's going to pop up on the screen in a moment, where the data has been sort of sliced vertically here, where the violation precinct is the thing that matters, and it's almost like, okay, everything with a low violation precinct is in one group, middle levels in other groups, and then high violation precinct number gets pushed into the blue group 1 here. That's actually kind of indicative of the pattern doesn't seem to depend on the feet from curb, so that there's not a strong relationship. And when there's not a strong relationship, we can see that the clusters can end up being kind of arbitrary depending on, again, those start points. When we scale the data and run it again, this time it chose to slice the data horizontally, right? So it groups all of the high feet from curb data together. The middle level and the low level gets split into two groups, one with a high violation precinct number and another with a low violation precinct number. So this is just, again, an indicator that it's maybe hard to know what to expect. I'll just run one more of these. This is feet from the curb versus vehicle year. So do newer vehicles have more issues with parking away from the curb or not. We're a victim of that issue with the vehicle year. Remember when we looked at the data, there was a huge number of zeros for vehicle year, which basically meant the vehicle year hadn't been entered, but it hadn't been entered as missing, it had been entered as zero. And so that really kind of messes up our results here. So that's a case where, to be complete, we really want to go back and clean up that data, get rid of the zeros, replace them with the missing NA. And if you don't do that, you end up with these sort of bizarre, arbitrary results. Although we might not expect there to be a relationship between the year of manufacture of the car and the feet from the curb. Maybe something that might be more reasonable would be if we took a look at the type of vehicle, like do trucks park further from the curb than sedans? That just an idea of a relationship to look at. And also just to point out that we can plot across multiple dimensions. We can kind of get a 3D view of this data. This is lines 442 to 451. And even the two-dimensional data, as we've seen, can be difficult to interpret. This is perhaps even trickier to interpret, but we can combine, multiple dimensions. So this data does not limit to just two variables. This is all of the variables in the data set, but we have, that actually combines some of those data. Oops, did I not run? I can see the full data set. So if we don't add the features, which limits the data to just the selected feature variables, then we will get the dimensional plot, that two dimensions that are combination vectors of other dimensions, and gives us a plot of other dimensions, and gives us a plot. I guess this could, tell us a little bit of, is there a strong clustering effect or not? Do we see separation? Here we see some overlap or close borders, so it's really quite mixed, these results. But again, another variant that is a bit tricky to interpret. Okay, so the final thing we'll talk about with k-means is the process of determining which k do we want, right? We've been doing a lot of this work where we said, okay, let's just try four centers. But there's an art to finding the correct number. And so what I'm going to do is generate a function. This is outlined on this link in the code, but create a quick convenience function to compute the sum of squares at each level of k, right? So we're going to iterate from k equals 1 obviously is meaningless. That's there is no clustering when you have only one center. But so we start from k equals 2, just looking at two clusters, and we're going to iterate up through 20 clusters, setting our max k to 20 on line 478. And we'll be able to compute the sum of squares for each of those k. So our convenience function on line 470 does that. We apply it for all the range of k in line 481 and save the result in a vector. And then we create a little mini data frame to represent those results so that we can then plot it. And the plot happens in lines 490 to 493. It's called elbow because what we are looking for typically is what's called an elbow, or a kind of kink in the curve where the results sort of flatten out. Now, as we add centers, we're going to reduce the sum of squares. this is just in the nature of things. It's just like in a regression, when you add additional variables, you can fit things better. But there's a trade-off. You get better when you add a variable. If it's not a significant difference, you may want to say to yourself, gee, it's better to keep the model simple, not try to overfit the data, and just rely on those variables that have a major contribution. So this is the same idea, except because of the randomness of the start points, the curve doesn't always go down in a continuous fashion. You sometimes have these bumps, right, where from 5 centers to 6 centers, the result actually gets worse. We explain less of the fit with 6 centers than we do with 5. It's a random artifact of the start points. But so we can see as we add start points, but so we can see as we add centers, for the most part, the variation drops pretty steadily until 10, and then bounces up again, then drops a bit more until 12. Then the improvement really sort of tapers off. Now, this again is going to be your judgment of like how important it is to get a really super fit, or how important is a simple, easy to understand model, right? If we are trying to, for example, cluster customers into different types, and you need to then explain to your sales force, there are 20 different types of customers. Here's how you deal with each of them. That's going to be harder than explaining 5 types or 10 types. So you have to evaluate, maybe 10 types is a good enough fit, and we'll stop there. And this sort of kink in the curve is something we can look at as an indicator of that. So that's place to stop. So we'll stop here with this discussion of k-means. And the next segment, we will get into a discussion of training and testing data. But let's pause here. Thanks for listening, and drop back in for the next segment. Okay, we're picking up with part 4 of the Machine Learning with Amaral series. Now we're moving on to training and testing, and getting into predictive aspects of machine learning. So up till now, we have been basically describing our existing data, and when we want to focus on prediction, we need to take a slightly different approach of a topic that has many different levels of treatment in machine learning literature, and different levels of treatment in machine learning literature and lessons. So often we don't have, or I would say always, we don't have data about the future itself. We have to pretend in some way that we are going to, we have an existing data set. Typically we have an existing data set. And we want to train a model on it. We want to build a model based on something we know about how that data works. But if we build the model on all of the data, then we lose the opportunity to see how the model performs on unknown data, meaning data that model has not seen it before. So it's again easy to overfit something if you are taking too much data as an input and not testing it on enough as an output. So what we do is we split the data that we have into what's called training and testing sets. The model is built off of the training data, and then the testing data that's been set aside is what we use to apply our model to, see what the predictions our model generates are, and then compare them to the reality of what was that data, what was in that testing data set. Here to a discussion of how this works. This works, and in this case, I think I will pull that link up so that we can have a better look at it. Called another aspect of this is cross validation, which we're also going to apply here. So validation is just in this case another word for testing. So the simplest way to do this would be to just do it once, to take our training data and testing data, setting aside the training data just one time. But we're missing an opportunity there. We actually have a full data set, and we can split that data a number of different ways. So in the image that you see on this blog page here, the data has been split 5 different ways. The first column, that first chunk of data, has been set aside as the testing data. In the second column, the second fifth of data has been set aside, and the other first, third, fourth, and fifth chunks have been used as training data, and so on up through the fifth chunk. It's actually labeled as K, but I'm just referring to what's on screen there as the 5 pieces. So this way we are insulating ourselves from anomalies in any one particular validation set. We're training the data. We're getting a training data grouping that's representative of the entire data, not just 4/5 of it. And we also have the advantage of being able to run our modeling 5 different times, which can insulate us against some of those random effects like we saw in k-means, that you run something once and it's a bit sensitive to the initial starting point. You get something not usual as your result. So we can set up the training and test splits a number of different ways. We can set up the number of iterations really as many times as you'd like, depending on your computational limitations. And there's again an art to this. You want to ensure that your training set is largish, but it's dependent, I think, more on the number of observations than the proportion of the data set. And the testing set also should be of a reasonable size, but it doesn't. There's no hard and fast rule for the percentage that you apply. If you have a smallish data set, you want to lean to having enough observations in your training data set that you can get meaningful results. So an 80-20 split, like we saw in this illustration, is reasonable for many cases, but it's not required. So for this section of data, we are going to again just restrict what we're looking at to a subset. So I'm eliminating a lot of the variables that are of interest to us, and a lot of the character variables as well. Let me just review here what we are getting rid of in lines 513 and 514. So we're not keeping the summons number. We're not keeping the plate ID. That's the actual license plate number. We're not keeping the issue date of the ticket. Unfortunately, in this data set, the date field is not numeric. It's actually recorded as a character variable, and it would also require a lot of cleanup to work with effectively if you were interested in changing patterns over time. But again, for this demo purposes, I'm not going to use that. The street codes, so we'd already gotten rid of some of this data in earlier steps, but I'm getting rid of it in the the big sample that is going to be the basis for things. So let me just run those commands. Again, it takes a little bit longer for the 42 million observations, although its performance is getting better, it seems. Called in machine learning lingo is called one-hot encoding. In other learning lingo is called one-hot encoding. in other variable. Let me pull up my little notepad here so we can. So I'm talking about one hot encoding. It's actually the same. It's actually the same thing as a dummy variable. If you've heard of dummy variables, which is the way that they refer to it in many social science disciplines, we are encoding our data in zeros and ones. So for the county, for New York City, we have Bronx, we have Queens, we have Kings County, which is Brooklyn, we have New York County, which is Manhattan, and we have Richmond County, which is Staten Island. Right. So if we want to do something that's geographically based, we'd want to convert these text fields into something that can be numerically incorporated into other processes. So for a parking ticket that occurred in the Bronx, what we would do is we'd have an indicator variable called Bronx. If something occurred in the Bronx, it would have an entry of 0. If it did not, entry of 0. If it did not occur in the Bronx, it would have an entry. Sorry, if it occurred in the Bronx, it would have an entry of 1. If it did not occur in the Bronx, it would have an entry of 0. Right. So original data. Let's say we had a few elements of original data like this. That would be converted, and we'd keep that original data. So we would then convert it into something like this. And I'm simplifying by not typing everything, but for Bronx, we'd have a 1 for the Bronx, but a 0 for the other counties. For Queens, we might see something like 1 0 0 1 0. For Richmond, we'd see something like 0 0 1. I've omitted the other two counties just for that quick example. So this can be done automatically by the function onehot from ML Tools. It's called onehot because it's encoded as a 1 or a 0, which is like a 1 or an ought in British pronunciation, and somehow that got slurred over to onehot along the way. Not exactly sure of the story of that, but that's so what I'm going to do is going to take the county. What I'm going to do is going to take the county variable and convert it to a factor. Factor meaning that in R it's been converted to a numeric representation, so that there's a 1, 2, 3, 4 encoding for that variable, and it's no longer just a pure text variable. And then I'm going to take that factor variable and also provide a one-hot encoding of it. County 2 as this new variable. Now I can do a new variable. Now I can do a table of working sample County 2, and it looks like this. So I have 43,000 entries with no entry, and notice this is a bit messy data, right? So we have BK, which is presumably Brooklyn. We also have K for King. So there's 88,000 Kings, one that's spelled out as Kings, and 9,600 Brooklyn. Now, if I need to clean this data and be precise about it, I should probably re-encode all of those Brooklyns and Kings to be all under K. But I'm going to be very sloppy here, and since there are not too many, the number that are actually K predominate, I'm not going to worry too much. I'm just interested in the general predictive results. But again, you want to be aware. This is something you want to be aware of when you're working with the data. The Bronx seems to be okay. gets encoded mostly as NY, but there's 1,000 MNs floating out there. Queens, again, we have some inconsistency, Q or QN, and Richmond and Staten Island, there's some blurry boundaries there too. So this is also very typical of real-world data, that one of your major issues is just going to be the data quality. Things are not standardized, and depending on how close you want to get to being perfectly clean, you're going to have to spend more time in cleaning up the data. All right, so now we are going to blend it into our future models, but I did want to introduce this topic separately, because it's something you'll often have to do with categorical data. All right, so now let's talk about the generic method that you might want to use to deal with this predictive data modeling. And there is a package called Carrot, which is the premier place for doing this kind of work in R. It's been around for a while. It has a lot of powerful features, and so I'm going to run through a built-in example using the IRIS data set, which is a very small data set of measurements of flowers. You may have seen it in other contexts, but just so we can do this at a small scale and run quickly, I'm going to do this example. So there's a function. All these functions that we're going to work with are from the Carrot package called create data partition. So create data partition lets us specify a proportion of the data. Here I'm saying 80% of the data is going to be set aside as the in the training data set data. Function called create folds. That's in line 529. That's in line 529. But in the examples I'm using, it's going to actually iterate on its own a number of times. So I'm not going to implement the folds right here by saying that the training data is the ones that have the row numbers in train. Data is the ones that have the row numbers in train, and the testing data are the complement of that, minus in train. If we want to see what this in train object looks like, we can see that it's actually just like a listing. Let's do the head of the in train. Numbers. It's not really in a format that is super readable on its own, but this is the 80% row numbers that have been selected. Use the train control function to fit the model different methods. So we're going to talk about the methods in just a moment, but CV here is cross-validation, right? So here I'm asking for 10 repetitions to cross-validate the model. And the nice thing about Carrot is, it takes care of all these details for you. So it can, it just kind of jumps in and does that. If we look at the names of this object that have been created, it's actually got a lot of things that it's done behind the scenes. And typically then what we would do is apply the result of train control to then finally actually train the model itself. So train, in this case, takes here we specify our model. So the outcome variable, the response variable, the dependent variable, whichever terminology you'd like to use, is first, followed by a tilde, and then the dot here means we're training it against all the other variables. So the entire rest of the data set is being used to explain species. Specify the data, specify the method. Now in this case we're using a random forest, that's RF. Random forest is actually kind of a combined method that iterates among several different options and then works to get the best blended outcome of those, often used with decision trees. So multiple decision trees create the forest. So again, what's great about Carrot is that it just implements this very transparently. You don't have to, it just implements this very transparently. You don't have to think too much about how it is iterating and doing all that. But that process is controlled by this fit control that we previously specified. So that the 10 iterations, the cross-validation method, is being applied thanks to our inclusion of this step. So let's run that. And you'll see that this does, even though this is just the iris data set, very small, 120 observations, it had to think for a moment, didn't quite pop back with an instant result. And what did we get? What is our fit model? So we have actually predict whether the flower is a setosa, is a versicolor, or is a virginica. A setosa is a versicolor or is a virginica. And we have basic statement of that, it's tried the model, it's cross-validated 10 times, and the parameter that was used was 3 as the optimal model. And the kappa here is the measure of the fit against the performance against the test data. The accuracy is the performance against the training data, which we hope that's good, but that's not really the final thing that we're interested in. Kappa is what happens when we push the model to our testing, and we hope that our original model, which performed well on the training data, will continue to perform well on the testing data and have a high kappa. And then we can examine the final model. This is line 539 in the code, which shows us what's called the confusion matrix, which illustrates how things have been classified. So there's an error rate of 4.17%. All of the setosas were classified as setosa, so that's perfect. Of the versicolors, 37 were classified as versicolor, but 2 were classified as virginica. So that's a virginica being classified. When we have a virginica that's a versicolor, that's an error. That's a false positive, if I'm not confusing my terminology there. And likewise for virginica, misclassified as virginica. So that confusion matrix gives us a sense of how things have been, how the performance of our model went. You can read more at the link here, which gives you a whole tutorial on cross-validation. And continue here, and we'll talk about the same methods, but applying it to our parking data. So I'm going to do the same thing, create a data partition, and in this case I'm specifying that the Y that I want to predict is the vehicle year. And I'm only going to take 1% of the data as training, 10%, excuse me, 0.1 proportion, because I have 420,000 observations in the sample. I don't want to again have something that runs really slowly. I tried this with the other proportion, and when you get into the cross-validation, you're repeating things 10 times. Even for our smaller data set, there's a bit of a lag here that I don't want to subject you to in video. But you can try it out. You can try out different proportions there. Split the data into training and testing, park train, park test. I specify my tenfold cross validation, and then run the model with the train function. And in this case, I'm also asking for a random forest as a method. And you'll see that this step is one of those steps that does take a little bit longer to come back with the result. So a lot of the details for you. We're going to see in just a moment the range of the number of models Okay, welcome back to part 5. The previous section, my computer did in fact get overloaded and the sound cut out for the last 2 minutes of the video. That is because it was busy doing processing and it had trouble recording at the same time. So in the meantime, I've kind of let that run on its own, and I'm just going to summarize the results here. We ran the model, and we have this fit. With a very low R-squared. It reports a little bit differently. It's got a root mean squared error, an R-squared, and MAE is not an indicator that I have worked with. But these figures are not absolute values. They are used to compare models to each other. So it's to some extent, we want to be careful and not switch to another model until we have something that improves the result. On the other hand, when we look at the final model, we can see there are 500 trees, but we only explained 0.12% of the variation. So that's not good any way you slice it. This particular approach of trying to explain the vehicle year has sort of revealed that there's no connection between the vehicle year and any of the characteristics of the parking tickets that are generated. So it's not like vehicles have a particular type of parking ticket or something that happens to them based on the age of the vehicle, and might be very sensible, but we can't really use this model to predict anything at this point. Now, in that example, I use the unscaled data. So I repeated that analysis with the scaled data on line 556, and I let this run. So I'm looking at RF fit 2 now. RF fit 2, again, we've standardized, we've reduced most of those numbers. That's not a number that is That's not a number that is again, directly comparable to the one we did before. We'd have to look at other scaled models with the same number of variables for the RMSE to be comparable. Our R-squared has improved maybe just a tiny bit, and we now explain, instead of 0.12% of the variation, we explain 0.18% of the variation. So an improvement, but a very tiny one. So anyway, this is more to illustrate to you how to run the algorithm in Caret. I'm going to run it again with a linear regression model. So this, we don't have to worry so much about scaling the data when we're running a linear regression. So I'm just going to use the data when we're running a linear regression. So I'm just going to use the non-character sample that we've had from before. The setup or the syntax of this is slightly different. We are labeling things a bit differently, but it's really the same train control, train functions. So we're going to just iterate 5 times. We're going to cross-validate 5 times. We're going to specify what our model is. So is the vehicle year related to the issuer precinct? Is the model we're trying to fit? Not trying to get too fancy with that. The train control result. Train control equals data control, which train control equals data control, which we've set up here, and the method LM is a bit more succinct process. It's going to still think for a little bit because we're running against 400,000 observations, but you notice it finishes a bit sooner. And here's our model. Again, this very sad-looking R squared returns again the same kind of observation metrics, and we can look at what the final model is in the same way by referring to that. So here's our intercept and coefficient on issuer precinct. So we do find some relationship. It's one of those R regression objects. So out, and it's significant, but once again the R square is really miserably small. So not a lot of explanatory power in what we've done so far. I've given you a link here with more about using Caret and up training and testing data in a little bit more training and testing data in a little bit more so let's run through this again. I think the repetition is helpful to get used to the way these are formulated. So we're using the same functions, create data partition, and we're going to use the train function in just a moment. So I'm going to train the row number, create an object called train row numbers by creating a data partition. This is based on feet from the curb, and I'm only taking 0.05% of the data, just because again I want something quick and responsive for this demo purpose. Create our training and test splits based on those train row numbers. In this case, I'm going to specify my x and y variables a little more explicitly. So the y is the response variable, feet from curb. The x is the other elements of the data set specified by the column number that I want to use as explanatory variables. And to show you that there are actually a number of different methods that can be used in Caret, I'm going to retrieve the model names with this get model info function, and there's so many of them that I'm just going to squeeze them together with the paste function so we can see them. These are all of the models that you can choose from. So Caret implements a huge range of machine learning methods. And so you can apply this training and testing split. You can run your models under the umbrella of Caret for all of these different methods, and you can go into the documentation and read more about each one of these. Obviously, there's almost too many there for any one person to master. But we're going to, at this point, look at the k nearest neighbors model. So this is actually a similar kind of concept to the k-means that we saw, but the k nearest neighbors is something that we use right. So the k-means clustering creates clusters, but k nearest neighbors puts objects into classes based on this algorithm. Now we can again use this to generate predictions just by passing it through the caret process. So that's what we're going to see here. All right, so I'm going to specify the method k and n. So here I'm just training x comma y. There's no cross-validation here. I'm not specifying that, but I'm training the model in k nearest neighbors. K nearest neighbors is a little bit computationally intensive also, so that's one reason that I want to keep my my proportion of data points small. This is something that would be very difficult to run against the full data set of 42 million without some real scoping out of how many resources you need. So I'm going to generate the model, then I'm going to use the predict function to generate the predicted values, and finally plot the model. So this is being trained again against the training data set, right? We specified x as trained data and y as trained data. But once we have those predictions, we will compare it to the test data coming up in line 612. And I'm hoping, there we go. So our model has completed its run. As it says, a large train of 20 elements, 6.5 megabytes. Take a look at the model. So here's the root mean squared error model. So here's the root mean squared error. It's one nice thing about this is that it does the checking for the optimal value of k. So k equals 9 was the optimal value that it determined. R square is much better than we've seen before, that there probably is some explanatory ability here. And here's a plot of how the root mean squared error changes as you increase the number of neighbors. When we apply this model to the test data, what are the predictions? When we apply this model to the test data, what are the predictions? Data is actually much larger. Remember, we trained the data on much larger. Remember, we trained the data on 5% of the complete data set. So the test data is 400,000 observations. That's why this step takes a bit longer. And when it's long like that, it always makes me wonder if it's time to stop the video or not, but I'm going to hang in there for another moment. There we go. So that wasn't too bad. It's much more computationally intensive to fit the model because there's a lot of unknown possibilities versus computing based on the existing model. And what do these predictions look like? They're actually, if you remember the feet from the curb, we had normalized it, and so a negative 0.14 like this is actually equivalent to 0 feet from the curb. Much of the data was 0 feet from the curb, so the first observations all look like they're pretty much in that category. If we look at this root mean square error, we can actually compute it directly via this RMSE function from ML tools and use that as a kind of guide to how we did. So you notice that in the training data, we had a root mean square error of 0.82, whereas we've done a little bit better even with the testing data. So the model didn't deteriorate when we applied it to the testing data, and that's another good sign, right? That things are okay. This might be a useful model to take, a useful approach to take. And I'm going to do one final thing here, which is to look at categorical data. And so I'm going to split my data into the data that is near the curb, meaning basically the 0 feet from the curb, and then everything else, right? To see if I can just predict something about whether the vehicle would be parked away from the curb or not. I do that by using this less than negative 0.14, which is pretty much equivalent to the 0 in the data set. And then I apply labels to it of false or true. Variable now just feet. I can see that it's true, right? So the trues are the ones that are 0 feet from the curb. Now we're just going to run this very same against the data, except we're using X data set. I think we need to see the model names again, but I'm going to fit it once again with k nearest neighbors. And the thing is that when we are, it's very similar to the previous model, because the measurements are the same, the underlying measurements are the same. We've just split it into two very simplified groups of 0 and everything non-zero. We have a little bit of a problem fitting the model. There's some warnings fitting the model. There's some warnings here. There are warnings is because some of these things don't apply in the same way to a categorical factor. So when we look at the model, we actually still get results. So before we still get this this plot, and can generate our predictions. Which is, again, is a slightly computational intensive step. Same numeric approach as before. I'm going to convert those predicted values. I'm going to convert those predicted values into factors in the same way that we did for the training data, so that we can then test it. So the prediction but we convert it back into a factor so that we have this true-false variables. So now finally what I can do is I can look at the confusion matrix on line 669, and this is really what I wanted to show you, was that you can get a confusion matrix for these caret generated model objects that look something like this. So here, parking tickets that were 0 feet from the curb, and we also predicted them to be 0 feet from. Were 0 feet from the curb, and we also predicted them to be 0 feet from the curb. There were 9,867 false negatives. We predicted they wouldn't be near the curb, but they were. There were 194 false positives that we predicted would be at the curb, but weren't. And there were 10,000 observations that were parked away from the curb, and we predicted that also. Right? So this cell is really the dominant one, and we've gotten most of those right. So the accuracy is 0.975, but the kappa is only 0.6656. Still, this is that's a decent level of prediction, unless the particular false positives or false negatives that you're very concerned about, where it's important not to make a mistake in certain categories. So we can also let's see a little bit of this data. However, the plot is, because we've got this factor variable that's either on or off, so we can see that across our other dimensions of data, and in this case we're looking at what are the names? This is issuer code versus the distance from the curb versus the distance from the curb. Is there a relationship? Well, for certain values there are no entries near the curb, but otherwise it's hard to make a strong pattern out of these categorical variables. So I'm not going to show more of the feature plot issues. So I'm going to stop here for this section, and we've seen that this is a little bit of a difficult data set to analyze. It's 42 million observations of somewhat messy real-world data with some limitations as to what it actually says. It's only about the parking tickets, so there's not a lot of interesting stories we can tell. Graphic analysis or time analysis here, so that limits again the approach we took. But what I'd like you to take away from it is just this general method that's available to you, especially the carrot package, which can manage your cross-validation, your training and testing split, and the model that you use, and put it all into a nice wrapper that you can then pull your results from and see how your model actually performs in a predictive sense. So I'm going to stop here. The final segment will be on neural networks, and it'll be a little bit different content to what we've seen right now. So thanks for Okay, welcome to part 9 of the Machine Learning with R series. This is Ryan Womack, data librarian at Rutgers University Libraries, and this will be the final segment of this series. This part, we're talking about neural networks. So neural networks are a method of filtering data through various nodes that are, in an idealized world, thought to be similar to neurons, and allowing models to iterate and converge over weightings across those nodes until a final best fit model emerges. These models have a kind of black box quality to them. However, they can be very effective for certain tasks. So it's a worthy tool. Now in R, there's a package called NNet. That is the classic R package for neural networks. Description seems promising. It has not been updated since 2019, and that makes me unupdated since 2019, and that makes me uncertain of its status, although I don't have any direct information about that. NNet is fairly simple. It does not capture a lot of the complexity that's possible with neural nets, but we're going to start there as a sort of standard, basic, classic version. And then I'm going to show you something else, which is H2O. So H2O is a multiple purpose machine learning engine. Does a lot of other things actually, but we're going to look at it for neural nets. So when we're working with neural networks, this is another machine learning method that requires normalized data. We've already done that in our previous segments, so that's fine. And with a number of layers, right? So the original data starts, right? So the original data starts, passes through a number of layers with a certain number of nodes per layer, and this is something that you can tune. That this allows the data to be fit to a wider range of situations, but as I said, it's kind of a black box. It's very hard to interpret what those weights on the intermediate stages mean. Often we just let the computer store those weights and ask the computer, hey, what do you predict for data that looks like this? Computationally intensive, so we have to be careful to limit our be parsimonious in how we do that. So I'm just going to start with a simple classic example using the iris data set once again. We are splitting it into training and test, as we have done before, creating an X and a Y. Here again, we're trying to predict species. And just as we did before, except we used a different method, you'll see this code looks just the same, right? We're using Caret to handle these details, but we're applying the NNet model, which has two parameters, size and decay. And we're just going to let the model run to do that. So we can see that it actually loops through several iterations and until it converges on values. It repeats that a few times, and then is going to give us a kind of average result. So the fitted data we can take a look at. Something that looks like this. This data is already been sorted to not be very random, so that's why our fitted data is all lined up like that. When we look at the model, there were 75 samples, 4 predictors, 3 classes, and we were able to achieve a maximum of 99.7% accuracy with final values of, so the 99.7% accuracy was achieved at size 3, and increasing that size to a size of 5 didn't improve it, right? So we stick with size 3, decay equals 0.1 as our tuning parameters. Different number of hidden units, hidden nodes, hidden units, hidden nodes, hidden units, and hidden nodes, hidden units, and we can check predictive power. Kappa is the terminology used here for the predictive value. Predictive kappa of 1 means it will predict things perfectly. So this predicts at a 99.5% accuracy. So accuracy is really fitting the existing data, and kappa is its predictive performance. Here in this model, they're very similar, but those could differ depending on the kinds of data. And so we are matrix, which will tell us, in this case, there's just one cell really that has things misclassified. Versicolor had a little trouble with things that were actually versicolor. 4 of them got labeled as Virginica, excuse me. Otherwise, the classification of Setosa was perfect. The identification of Virginica was perfect. All the Virginica were correctly identified, plus some of these false positives for Virginica. So that's another use of the confusion matrix. So this is as we see, the NNet method is nice. It's simple. It's straightforward, but it doesn't let us do much else with the tuning of the neural net. So this again is not an area. I'm not a super expert in this. I'm trying to expose you to some tools that are out there, with the hope that you may delve in and go further. But one of the things that I found when investigating this was H2O. So H2O is it's not R only. It's not an R package. It is its own software tool, and it covers multiple machine learning approaches. It is parallelizable, so we can make use of multiple cores for our computations. This makes it a good choice for things like working on a high-performance computing cluster. We would launch it with this H2O init, but this requires us to have a number of other things installed. So what I'm going to do is talk a little bit about that installation process, and the connecting it to your RStudio is a little bit of a different animal. The H2O project itself is at h2o.ai. As you can see, making world-class AI models and apps. And if you go to open source, you can get access to the platform itself. So this download latest. You can download H2O. It's just a zip file. It's a zip file that runs this Java installer. So you can download, run these scripts, and unzip it. And then you'll have on your local browser, it opens up a port that allows you to start to do work in the browser like this. So we can import files, we can build models, we have various navigation menus that allow us to pick specific models. And if we go to, say, deep learning, we can select algorithms. We have all these parameters, and this is an example of something where we can get into much more fine-grained tuning. As you can see, it's quite complex in its presentation. So this is sort of the next stage that you may want to think about for a kind of a Jupyter notebook approach where we can enter code in cells, right? So we can add a cell, and when I go to run the cell, which I can run with the Control-Enter abbreviation, it's going to provide the assistance to me. So you need to bring data in to this environment, which I can do using the import files, and then I can start to work with it in this setup. And we can tap into this from R certain H2O commands that we can access as well. But this package for H2O within R connects us to it, right? So we for H2O within R connects us to it, right? So we can. Problem is that H2O does not read R files directly, so we have to kind of dump the files directly. So we have to kind of dump the to CSV format. And I just want to see where my working directory is. I'm going to modify this path, and I just want to see where my working directory is. I'm going to modify this path to be something a bit simpler. Your and let's try this out. So I'm going to write the CSV file for the training data. I'm going to write the CSV file for the test data. And then I'm going to ask H2O to upload the file. And this warning message not going to get in the way of this functioning for right now. I might need it. I tried to reinstall, but it might need a complete reboot before it'll recognize that, which I don't want to do given all of the data that I've got loaded in right now. Okay, so you can see that this H2O upload file has imported those data items, and now we can invoke H2O. So we can invoke the deep learning unit, and we have access to additional parameters here. We have a training frame, we have a validation frame. So that's really training and test, right? That's a little bit different terminology, calling it the validation frame. And we can specify help for deep learning at X and Y are index vectors, columns 1 through 4, and our response variable is column 6, that's Y. Our response variable is column 6, that's Y. And you can see that we could, all of those things that we saw in the graphical menu on H2O are things that we can specify via text commands as well. So once again, this is just not an area that I have any experience in, any advice to give you about how to set this up. But H2O is a leading way to deal with these issues, and obviously gives you a lot of options to set those. So if I start to build my data here, you can see that this neural network, again, is computationally intensive. Even though we have our small training data, it still takes a little while to iterate and run that model. No, that's not. So this is a sort of unhappy result here. To generate anything useful. And I don't know, maybe this is now my lack of an useful. And I don't know, maybe this is now my lack of an update is coming back to catch me. My model is not defined. Let's just look at my model. Be present in your updated version as soon as I submit these changes. Updated version as soon as I submit these changes. My approach to try to find the names did not work for H2O, but the model did run. You can see when we just type my model, we get this output describing what happened. We have these 4 layers, then various parameters that discuss and this is where again I don't find these parameters to be something you can interpret directly. It's very interactive with the other nodes, and it's just not something you can just look at and make a judgment on it. However, we can see that we by comparing their RMSE stats as we usually do. So on SE stats as we usually do. So on the training frame, we had an RMSE of 0.97. When we validated the data, that bumped up a bit to 1.0, but not too much of a change. And if we had alternative models, we could compare on the basis of RMSE, which one is better. It requires a little bit of wiggling around, right? So if I want to, predict function on the basis of the test data, then I convert it to a data frame, the test data, then I convert it to a data frame because it doesn't come in as a data frame. I'll take the test data itself as a data frame, and now I can plot those two things against each other, so I can see how my predictions are performing. And that may take a moment to generate. Here we go. All right, so I have categorical data that we had just been working with. You could You could experiment by going back a step. And using the non-categorical data. But here we have the data that is either has some distance from the curb. That's our sixth variable. Remember, feet from the curb. So our sixth variable, remember, feet from the curb. So we can see that the prediction doesn't really, I mean, from this level, we can't really tell much of a pattern, right? We could see a strong pattern if there were, like say, low predicted values associated with the left-hand option of close to the curb and high predicted values associated with the right-hand option. And that might indicate a way to get a better fit or a better prediction. Here there's a lot of overlap, but that's, all overlapping on this categorical graph, so it's not really super interpretable. So as I mentioned, I'm not like an H2O expert. I'm not a neural net expert, but I want to point you in that direction if this kind of thing interests you. Here are a couple of links in the code that talk about how to work with H2O in combination with R, and how to work with H2O for large data sets, because I think this is, like a number of projects, very promising. Certainly not the only way to get this kind of work done, without even getting into Python for machine learning, but it's one method that will handle neural nets via the deep learning options. And as we can see, there are a number of other models that you could also use this tool for, if that's your thing. Also, just an example of, for the newer tools, you have this process of adaptation where R begins to latch on and start to make use of them, over time, functions develop that make it much more seamless to pass data back and forth and make use of those other tools until you get something like the carrot implementation of this might make it almost a one-step process without additional installs. And it's how R tends to evolve over time. So this has been a longer session, partly because of the data, partly because of the number of things that we've been looking at. I want to thank you for your attention. If you've made it this far, that's fantastic. I hope that you continue to learn about data, learn about machine learning, learn about R, and just keep improving your skills. So thanks again, and wish you success.